Hello students, myself Mrutyunjay SME, faculty, Department of MCA, KLS Gokte Institute of Technology, Belagavi. Welcome you to this PGCET awareness program. So today I will be covering about the data representation and the binary arithmetic under computer awareness section of your PGCET question paper. So let us start with data representation. So in this entire data representation and the binary arithmetic, you will be getting almost say 6 to 8 1-mark questions and almost 1 to 2 marks questions. So totally it is making up of 8 to 12 marks, 12 marks in the PGCET question paper. So let us start with data representation. So now in this particular case, why we want the data representation? Data representation. So why it is required? So in this particular case, you already know that computer is going to process the data. So before processing, it has to store the data in a computer memory. So in order to understand the processing part, first we need to understand how the data is stored. So for this particular sake, the data representation comes into picture. So with respect to data representation, the meaning is that there are two viewpoints here. One is internal representation, one more is external representation. Internal representation means how the data is stored into the hardware of the memory or hardware of your computer. So this is what the internal representation. External representation means how the computer is going to display the output or the data to the external world, means to the users. So this is means the external representation. So the conversion from the external representation to internal representation and back from internal representation to external representation, this process is known as a data representation. So in this case, as I have told, that the external representation. So consider I am writing a program using any general purpose language. Say I want to write a program to sort the given name of students. Okay. So in this particular case, what is my input? The input is the student names. So I will take the input, the student names. So in this case, student names are the inputs taken from your keyboard or from any other input device and which will be stored into a memory. And then the processing part is what in this particular program? Sorting. Okay, sorting according to the alphabetical order and then print that particular alphabetical order or sorted order onto the output display device or to the printer. This is the process here. So in this case, giving an input to a program is external to an internal representation. And internal representation, what I can say, the internal representation to external representation is processing that those particular names and then presenting the output to the external world is called as an internal to external representation. So in this entire process, okay, in what form the computer is going to understand the data? Okay, so as an external world, we as a user, we understand the numerals and characters. Okay, numerals are nothing but the decimal number system we understand and the characters, okay, alphabetical characters from the English statement or English language you can say. Then but your computer doesn't understand this decimal number system or what I can say the characters. So now for computer hardware, whatever the data is being represented, it is represented in the form of a binary only. So this clearly tells that your computer hardware will understand only two types of symbols, that is 0 and 1. Okay, so this is our binary input or binary symbols, you can say. So whatever the data that we want to convey it to a computer, it is in the form of zeros and ones only. Okay, so this is your internal representation. But to the external representation, when it is to be presented to the user, it should be decimal format, or it is in numeral format, alphabetical format. Okay, so this is why the data representation is plays a very important role in our computer hardware. So let us begin in this particular case with the data representation aspect. So data representation includes various number systems. Various number systems. So as a human being, we understand the decimal number system. So already you, from your childhood, okay, from your school days onwards, so far you are dealing with the decimal number system. So what is decimal number system? Decimal number system, you have 10 symbols to represent any number. Okay, so already you know that. So what are the symbols? Symbols are nothing but 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 to 9 symbols are used to represent our decimal number. But your computer doesn't understand 0 to 9. So it is to be represented in the form of 0 and 1 only. Okay, so because of this particular reason, let us see how the conversion takes place from decimal to binary number system. So similarly, as I have defined what is decimal number system, in the same manner we can define binary number system also. That is nothing but our binary system is nothing but it consists of two symbols, that is 0 and 1 only, and it is having a radix or base as 2. This base is also called as radix. Radix or base 2. Okay, so our decimal system is having a radix 10. These are the nomenclatures that are used in the number system. So by identifying the radix, we can understand in what number system the data is represented. Okay, so this is for our understanding. Okay, so let us begin now how exactly the conversion takes place. So let us take one example here. So I have a one decimal number 41, which is represented in decimal format with radix 10. So now I need to convert it to the binary number. Okay, so this is the conversion. So I have a decimal number which is to be converted to a binary. So in this particular process, what you do? You write down the number, given number as it is, and just go on dividing this particular number by 2. Okay, so continue this particular division process until the quotient becomes 0, and keep track of the reminders generated in this entire process. Okay, so let us continue now. So in this case, the reminder generated is 1. Reminder is 0. So finally 0, 1. So now this is our quotient becomes 0. These are the reminders generated. Okay. So I have continued this division process by 2 till I reach 0. Okay. So quotient has become 0 now. So I have kept track of the reminders generated in this process. Okay. Then write down these reminders from bottom to top. Okay. So in this particular case, 1 0 1 0 0 1. So this is our equivalent binary number. So given decimal number is 41 and its equivalent binary number is this one. Okay. So in this case, this rightmost bit is called as least significant bit, LSB, and this leftmost bit is called as MSB, that is the most significant bit. Okay. So in this particular case, this bottom number is your MSB and this is your LSB. So in this fashion, you need to reorder the binary number. Okay. Right. So let us do the reverse operation, that is binary to decimal. Binary to decimal operation. Okay. So the binary number will be given. You will be asked to generate the equivalent decimal number. So let us consider the number, binary number as 1010.011. So this is the given binary number. You are being asked to generate an equivalent decimal number. So when we are dealing with number system, already you know that there are two parts. One is integer part, second one is the fractional part. So in this particular case, in the earlier example, I have taken only the integer part. So in this case, I have taken both. This is our integer part, this is our fractional part. Okay. So this, since we are dealing with the binary number, this is known as a binary point. In decimal number, this is called as a decimal point. Okay. Right. So now in this case, just write down these particular number. Okay. Means whatever the given number, you need to express in this case. So express the given number as a polynomial of 2. Okay. So in this case, 0, let us write down the integer part first. 0 into 2 raised to 0. Next number is 1 into 2 raised to 1 plus 0 into 2 raised to 2 plus 1 into 2 raised to 3. So 0, 1, 2, 3. So there are 4 digits. Start from 0 for the integer and it will end up in 3 for 4 digits. Okay. So this becomes our integer part. So for fractional part, same as 0, first number is 0 into 2 raised to minus 1. Okay, it is a fractional part. As with the same rules that are applied for the decimal, also here for binary. 1 into 2 raised to minus 2 and one more digit is 1 into 2 raised to minus 3. Okay, so express the given number as the sum of power of 2. So we have expressed the given binary number as sum of power of 2. then just simplify this polynomial. That's it. Okay. So let us see. So 1 into 2 raised to 3 is 8. 0 into anything is 0. So this is 2. 0 into anything is 0. Plus this is 0 only. This is 1 by 2. Sorry, 1 by 4. And this is 1 by 8. Okay. So if you simplify this, you will get 10.375 as the equivalent decimal number. Okay. So we have seen both decimal to binary conversion and binary to decimal conversion. Okay, with respect to binary number system and decimal number system is concerned. Okay, so let us continue this particular process. So now one more what I can say the number system I am going to discuss now, that is octal number system. Okay, so similar to decimal and binary number, octal number system also is having two parts, that is integer part and fractional part, which are separated by an octal point. And also in this particular case there are 8 symbols which are exclusively used to represent any number in octal by number system. Okay, this rule applies to all the number system. Okay, so now which are the symbols that are available in octal number system to represent any number? So here I have listed. Okay, so 0 to 7. So these were the 8 symbols which are exclusively used to represent any octal number. Okay, so only 8 symbols are available. With respect to binary, only 2 symbols are available, that is 0 and 1. With respect to decimal number, 8 symbols are available, that is from 0 to 9. And octal number system, we have 8 symbols are available, 0 to 8. Okay, so let us see now how to convert the given decimal number to an octal number. So consider a decimal number as 153, and you have been asked to generate the equivalent octal code. So in this particular case, the process is very much same, that is a decimal to binary conversion. How we have done, the same rule is to be applied in this case also. Okay, that is the division process. So write down the given decimal number and go on dividing it by 8. Okay, so you continue this division until you reach the quotient as 0 and keep track of the remainder generated. Okay, so the same rule is to be applied, only the divisor is 8 in this case instead of 2. So here it is 19. So remainder generated is 1, and again 8 into 2, 16. It is remainder generated is 3. So 8, 0. This is 2. Okay. So this is your most significant bit, you can say, MSB. This is our least significant bit. Okay, means what? The equivalent octal number is 2. First one is 2. Okay, that is the leftmost side. Next number is 3. The last number is 1. So this is our LSB and this is our MSB. So 231 is an equivalent of 153. Okay, right? So let us see the reverse operation of this octal to decimal. So consider the octal number 630. Okay. So let us see why I am calling it as an octal number. Because see, the number is framed or devised using the symbols of the octal number system. What are the symbols that are used in octal number system? Starting from 0 to 8. So see, we have 0, yes, we have 3, we have 6. So all these are the symbols of octal number system. So you have been asked to convert it to an equivalent decimal number system. Okay. So now again the same process in this case. You have to express the given octal number as a polynomial of 8. Means you have to express the given octal number as a power of 2 and then simplify it. Okay. So here 0 into 8 raised to 8 raised to 0, 3 into 8 raised to 1 and 6 into 8 raised to 2. So you have expressed the given octal number as a power of 8 and then simplify it. Okay. So if you simplify this particular arithmetic, you will get answer as 408. Okay. So the same rule, whatever we have used for binary to decimal conversion, the same operation is been used in this particular case also, except that the radix is to be changed. So if it is binary, we have to use the radix or power as 2. In this particular case, since it is an octal number, we have to use the base as 8. Okay. So this is the point to be noted in this case. Right. With this, next I am going to introduce you one more number system, which we call it as hexadecimal number system. Hexadecimal number system. So what is hexadecimal number system? Hexadecimal number system also consists of 16 symbols. That's why the name is hexadecimal. So here any number is represented using 16 symbols. Okay. So here starting from 0 to 9 and then A to F. So these were the 16 symbols exclusively used in hexadecimal number system to represent any number. Okay. That's why the name is hexadecimal. So in binary we have 2 symbols, in decimal we have 10 symbols, and in octal number system we have 8 symbols, and in hexadecimal we have 16 symbols. Okay, 0 to 9 and capital A to capital F. Okay, right. And also in this case, with the normal number system regulation, decimal number rules and regulations applies here also. Okay, so it is having an integer part and fractional part also, and these two parts are separated by hexadecimal point. Okay, right. So let us see the conversion process from decimal to an hexadecimal, decimal to an hexadecimal. So consider a number 41819 as a decimal number, and you have been asked to convert it to an equivalent hex number. Okay. So again in this particular case the process remains same as with respect to decimal to binary and decimal to an octal. The same procedure you need to use, only the change is that the radix. There in binary, decimal to binary we have considered 2, decimal to octal we have considered radix as 8, in the hex we need to consider radix as 16. Okay, so this is the point. So write down the given number, decimal number, and go on dividing it by radix 16. Okay, and keep track of reminders generated in this process till the quotient becomes 0. Okay, so if you go on dividing it, you will find the remainder as 1 in first step, second one in second iteration we have remainder 5, and in third iteration we have remainder 3, and the last iteration we have remainder 10. So now the quotient has become 0 in this particular case. Okay, so again this is our MSB, most significant bit, and this is our LSB. So therefore our answer is 10. Okay, so we are representing hexadecimal number system. Okay, in hexadecimal number system. So hexadecimal number system, we don't have 10 and 11 there. Okay, so that's why I have written the symbols here. So what is in decimal 10? In decimal 10, the equivalent hex code is A. Okay, so here only you can write down. So this is our capital A. And what is 11? So 11 equivalent 11 is our here in the decimal number 11 is B. So this is our B. So therefore most significant bit is capital A. Next digit is 3. 3 is available, and 5, and the last one is that is 11, which is B. So this is an equivalent hex number. Okay. Okay. So let us do the reverse process of this, that is hex to decimal. So you will be given an hexadecimal number, you have been asked to convert it to a decimal number system. So let us consider the hex number as B65F. So this is the given hex number. You will be asked to convert it to an equivalent decimal number. So in this particular process, again the procedure remains same thing. You have to express the given number, given hex number as a sum of power of 16. Okay, so F into 16 raised to 0. Next digit is 5 into 16 raised to 1. Next digit is 6 into 16 raised to 2. And next one is B into 16 raised to 3. So I have expressed the given number as the sum of power of 16. Okay. Now simplify this. So before that I need to convert the symbols to an equivalent decimal number. So what is B? B equivalent decimal number is 11. So this is 11 into 16 raised to 3. 6 is as it is. 5 is as it is. Plus F is nothing but 15 in decimal. 15 into 16 raised to 0. So if you simplify this, you will get the answer as 46687. So this is the equivalent decimal number. Okay. So far binary number system, octal number system, hexadecimal number system, and equivalently the decimal number system. So we are well versed with these particular number systems. So let us see few more conversions with respect to these particular number system is concerned. So let us consider the conversion from binary to octal number. Okay, so you will be given a binary number, you will be asked to convert it to an equivalent octal number. So I will write the binary number first. Given binary number 1011 000 11 01 011. So this is the given binary number, and you have been asked to convert it to base 8, that is octal number digit. Okay. So in this particular case, what you need to do is, this is our least significant bit and this is our most significant bit. Okay. So now consider the given number and start or make the group of these particular binary bits. Okay, starting from LSB. So you need to make a group of 3 binary bits starting from least significant bit. So this is our least significant bit. So start making the 3-bit group from least significant bit to most significant bit. Okay, so let us do this first. So I am starting with least significant bit. So this is my first group, this is my second group, this is my third group, and this is my fourth, and remaining is the last one. Okay, so I will write down these groups separately here: 011, 101, 001, then 011, then finally 01. Okay, so if you add any number of zeros at the left hand side, okay, it will not alter the meaning of the number. Okay, so the rule is same for all the number system. This rule we also follow in decimal number system also. Okay, right. So in this case, just now you have made the group of 3 bits. Just replace each of these 3 group units with equivalent octal number system, octal symbol, you can say. Okay, so just see here, this is our octal system. So 0 to 7. So 0, 1, 1. Okay, so just look at the binary, what I can say, the code here. So 0, 1, 1. So this is our 0, 1, 1, which is nothing but 3 in octal number system. So this represents 3. Replace this 3 good word with equivalent decimal number. Okay, or octal representation. Then 101 is nothing but 5. And this is 1. 110 is your 6. Then 010 is 2. This last one, if you add this, it will become 3 bits. So overall, we can say that 26153 is an equivalent octal code. Okay, just remember, from least significant to most significant bit, you need to group 3 binary numbers. Replace each 3 bit binary group with its equivalent octal symbol. That's it. Okay, right. So similarly, We have seen binary to octal. Now binary to hex. Let us see how we can do it. Binary to hexadecimal number system. So here the given binary number is something like this: 1011 000 11 01 011, which is our binary. We have been asked to generate the equivalent of hex. Okay. So in this particular process, again the same procedure as we have done earlier. Instead of making a 3-bit binary group, here we have to make 4-bit binary group starting from least significant bit to most significant bit. And replace each 4-bit group with its equivalent hex symbol. That's it. Okay, so let us do that. So this is my first group starting from LSB 1011. Next group is 0110. Next group is 1110, and last one is this 10. If you add any number of zeros at the left hand side, it will not alter the value. So let us, so I have written the chart here, the different symbols of number systems. So 1011, okay, so 1011, so this is our binary 1011. Its equivalent hex is B. 0110, 0110, where it is 0110 is yeah, it's here 6, that is 6. Then 1100 1100, which is nothing but 12 in decimal number. Its hex representation is C, and this is 2. So 2C6B is an equivalent hex number. Okay, the procedure remains same in this particular case. Okay. So now let us see the reverse process of these two methods, what we have discussed. So next conversion is, you will be given an octal number and you need to convert it to a binary. Okay, so consider the octal number as 673 and you need to generate an equivalent binary number. Okay, the procedure is very simple here. This is the given number, write down as it is. Okay, just replace each of these octal digits with its equivalent 3-bit binary number. That's it. Okay, so here I have already written here. So 3-bit binary code for number 3 is what? Octal number 3 symbol 011. So 011. 7 is 111. 6 is 110. So if you combine all these things, it becomes an equivalent binary number. So it is very simple. Similarly, let us see octal to hex. Octal to hex conversion. So you have been given an octal number 345 and you will be asked to convert it to an equivalent hex number. Okay, So write down the given number. Okay, this is the given number 345, which is in oct. Okay, then just represent it's a 3-bit equivalent oct, what can say, the binary number. Okay, 5 is what? 101. 4 is 100 and 3 is 011. Okay, what we have done, we have written the numbers, octal numbers as it is, and just we have represented its equivalent 3-bit binary number. Okay, and then now what you need to do, you start grouping this entire binary number starting from least significant bit, move towards most significant bit. And in how many numbers you need to group? 4 bits. So you need to make 4-bit group starting from least significant to most significant bit. Okay, so this is my first group, this is my second group, and remaining is 0. Okay, so if I write that particular thing here for your understanding, 0, 1, not 1, this is my first group, second group is 1110, this is the second group, last group is 0 only. Okay, so now replace each of these particular 4-bit group with its equivalent hex symbol. Okay, so 101 is nothing but 5 only. Okay, next is 1110, which is nothing but E, and 0 is 0 itself. So overall 0E5 is an equivalent hex number. Okay, so these are the various conversions that we can consider under the data representation, which your computer or CPU uses for the data processing tasks. Okay, apart from that, this we have different kinds of what you can say, the codes that exist in this particular case. Amongst that, the first one is ASCII, next one is abscisic. So these are the standard binary codes which are exclusively used for data representation in our computer systems. Okay, so ASCII means American Standard Code for Information Interchange. So just remember these full forms which will be asked in the examination. ASCII, American Standard Code for Information Interchange, and this particular code is of 7-bit long. Okay, so 7-bit binary codes are used to represent any ASCII characters. Okay, so if 7 bits are used, means what? Overall 2 raised to 7 possible code characters are available in this case. So 2 raised to 7 means 128 character codes are available. Codes are possible in this particular case. Okay. Similarly, the next one more standardized code is abscisic, which is nothing but extended binary coded decimal interchange code. Okay, extended binary coded decimal interchange code, and this particular code is of 8 bits long. So if it is 8 bits long means 2 raised to 8 possible code characters are available. Means a total of 256 character codes possible. Okay. So this much is sufficient for the data representation. So I hope this particular information is helpful for preparing the data representation aspect of your computer awareness, what you can say, the questions concerned. Okay. So thank you very much.